So November 30th, 2022.
Right?
That's the day a simple chat interface went live on the internet and just, well, it fundamentally altered the trajectory of human technology.
Yeah, it really did.
But if you listen to the popular narrative today, that launch is treated like this sudden magic trick.
Oh, totally. Like an overnight success.
Exactly. The story usually starts with that famous 2017 paper out of Google, the one that introduced the transformer architecture, and then poof.
Just a time skip.
Right. We jump 5 years into the future, some brilliant engineer types the final line of code, hits enter, and boom, ChatGPT is born. But there is this massive, incredibly messy 5-year gap in that mythology, and the reality of what actually filled those 5 years, well, that's the mission of our deep dive today.
Yeah, because that gap between the theory in 2017 and the actual product in 2022, it represents, honestly, one of the most brutal engineering marathons in history.
Yeah.
We are talking about a completely unglamorous, high-stakes industrial grind that is, almost entirely invisible to anyone who actually uses the final tool.
So to really pull back the curtain on this, we are unpacking a brilliant essay published today, May 29th, 2026, in Tech Reader magazine by Aaron Rose.
Really great piece.
Yeah, it's titled How ChatGPT Was Built, Part 2, The Engineering Challenge That Made It Real. And okay, let's unpack this because reading through this material fundamentally broke my mental model of AI development.
How so?
Well, I went in thinking that building ChatGPT was like writing a particularly clever operating system, right? Just really good code. But the author paints a picture where it's more like, imagine deciding you want to build the world's tallest skyscraper.
Okay.
But then you realize you first have to spend years inventing the manufacturing process for industrial steel and building the foundries and paving the supply roads before you can lay a single brick.
That framing captures the scale perfectly, because Rose's essay argues that by late 2017, the foundational theory was, well, it was already known.
The math was there.
Exactly. OpenAI didn't have a theoretical research problem on their hands anymore. They faced a systems engineering problem at a magnitude humanity had, frankly, never attempted to coordinate.
So let's start with that steel manufacturing, right? The raw materials. Because in the AI space, you can't just plug a transformer model into a wall, connect it to the internet, and expect it to learn to speak.
No, absolutely not.
Before a single artificial neuron fires, you have to build this colossal, flawless data pipeline.
Because, and this is a key point, a transformer algorithm doesn't actually understand text.
Right.
It doesn't know what a word is. It has no concept of a sentence, and it certainly doesn't understand the meaning of human language. It only understands numbers.
Yes, math.
Right. Specifically, it understands tokens, which are these numerical fragments.
And I always picture tokenization as just like swapping a word for a number, like a secret decoder ring.
That would be too easy.
Right. But the reality is much weirder. Because a single word, like understanding, might be chopped into 3 entirely different tokens based on its syllables or letters.
Yeah, they needed a system to chop up human language in a way that the computer could mathematically process, but without losing the nuance of how words connect.
Which is where byte pair encoding comes in.
Exactly. BPE. Instead of storing a unique number for every single word in the English dictionary, which, by the way, would create an impossibly massive vocabulary for the model to search through BPE, scans the raw text and looks for common visual patterns.
So it's looking for chunks of letters.
Right. It groups frequent letter combinations together. So a common suffix like ing or tion gets its own dedicated token.
So it basically compresses the language down to its most efficient building blocks.
Exactly.
And that way, the vocabulary is mathematically compact enough for the hardware to process, but still expressive enough to capture everything from, obscure legal jargon to internet slang or even lines of Python code.
Yeah. And what's fascinating here is that implementing BPE is just the formatting stage.
Just the formatting.
Right. Before you format the data, you have to find it, scrape it, and violently scrub it clean.
Violently scrub it. I like that.
It's true. The engineers had to build automated web crawlers to pull down a significant fraction of the entire internet. Then they had to build these heuristic filters and independent classification models.
Like digital bouncers.
Exactly, bouncers. Their only job was to kick out spam, low-quality text, gibberish, and, of course, highly toxic material.
And even after you clean it, you still have the deduplication problem.
Oh, the deduplication is crucial.
Because, think about it, if I'm setting for a biology test, right, and I read the exact same textbook paragraph 1,000 times, I'm not actually learning the underlying concepts of biology.
You're just memorizing the word.
Just memorizing that specific sequence of words.
And a neural network operates the exact same way. If a specific chunk of text, say a standard software license agreement, appears millions of times in the training data, the model's mathematical weights will just over-index on that repetition.
It gets lazy.
Basically, yeah. It stops trying to learn the abstract rules of grammar and just hard codes that specific string of text into its memory.
So to prevent that, you have to meticulously deduplicate the entire internet.
Which is insane. You need distributed storage infrastructures capable of comparing billions of documents against each other to remove the duplicates before the training even begins.
And the scale of what survived that gauntlet is just staggering. Rose notes that the final filter dataset used just to train GPT-3 was around 45 terabytes of plain text.
Just massive.
That equates to about 300 billion tokens. If you tried to read that much text as a human, it would take you hundreds of thousands of lifetimes.
And if you compromise on the quality of that 45 terabytes, no amount of brilliant AI code can save you. A faulty data pipeline that lets in repetitive or corrupted text, it permanently brain damages the final model.
Okay, but I actually want to push back on something Aaron Rose claims here, because he uses this farm-to-table analogy, right, where the data pipeline is the agricultural supply chain, and the AI code is just the chef in the kitchen.
Right.
He actually rates the difficulty of building this data pipeline an 8 out of 10.
He does.
Wait, if gathering and sorting the text is an 8 out of 10, is he suggesting the supposedly world-changing AI code was the easy part?
He is suggesting exactly that.
Really?
Yeah, he rates the core mathematical recipe, the actual Python code for the transformer architecture, as roughly a 3 out of 10 in difficulty.
A 3 out of 10.
Yeah. A competent machine learning engineer could write a functional, basic transformer in a few hundred lines of code in an afternoon.
Wow.
The architecture itself wasn't the hurdle. Executing that architecture across hundreds of billions of parameters using wildly unpredictable hardware, that was the hurdle.
Which explains why they didn't even use Google's original 2017 code.
Right.
The essay mentions Google built their transformer using a framework called TensorFlow. And OpenAI completely scrapped that. They rewrote the entire thing from scratch in PyTorch.
They did.
And while they were doing that, they surgically altered the fundamental design of the engine.
Because the 2017 paper designed the transformer for language translation, like turning English into French.
Okay.
And because of that, it had two halves. It had an encoder to read and analyze the English, and a decoder to generate the French. OpenAI made this radical decision to just strip out the encoder entirely.
They just amputated half the architecture.
Basically.
Because they didn't care about translating specific inputs. They were betting everything on causal language modeling.
Which is just a highly technical way of saying they wanted the machine to play the ultimate game of guess the next word.
Right. The objective became almost ridiculously simple.
Yeah, you give the model a sequence of tokens, and it calculates the mathematical probability of what the very next token should be.
There are no categories, no labeled data, no distinct tasks.
Exactly.
Yeah.
It just looks backward at what was already written and predicts the immediate future. And to enforce this, they implemented a mathematical filter called a causal mask.
A causal mask.
Yeah, which literally blinds the model to any tokens that come after the one it's currently trying to predict.
It physically cannot cheat by looking ahead at the answer.
Now, conceptually, predicting the next word sounds simple. But taking that stripped-down decoder and scaling it up turns out to be an absolute nightmare.
Oh, a total nightmare.
Because when OpenAI trained GPT-1, they used a few dozen graphics processing units, or GPUs. But fast forward to GPT-3, and they are trying to link thousands of GPUs together to run continuously for weeks.
And this is the transition into a 9 out of 10 difficulty infrastructure challenge.
Yeah.
GPT-3 was built with 175 billion parameters. Those are like the artificial synapses of the network. A model of that physical size cannot fit inside the memory of a single graphics card.
It's just too big.
It is physically impossible.
So you have to shatter the model into pieces. Right. That process is known as model parallelism. You slice the model's structural layers and distribute them across different physical machines.
Okay.
But simultaneously, you are trying to feed it those 45 terabytes of training data, so you also have to slice the data batches and distribute those across different groups of machines.
And that's data parallelism.
That is data parallelism.
I mean, trying to visualize that just gives me a headache. You have thousands of processors handling different fragments of the brain, reading different fragments of the internet, and they all have to synchronize their mathematical updates millions of times a second, without dropping a single connection.
It is the ultimate cathedral of distributed computing.
Yeah.
And the floor of that cathedral is basically covered in landmines.
Right. The essay highlights this constant looming threat of mathematical instability during these training runs.
Yes, because the network learns by updating its parameters using gradients.
Gradients.
Yeah, think of them as directional steering signals that tell the model whether its last guess was right or wrong.
And those steering signals can suddenly just snap.
Oh, constantly. The engineers would be watching the training metrics, and out of nowhere, the gradients would either explode into massive, unmanageable numbers, or they'd collapse completely to zero.
Meaning the model just stops learning?
Stops learning, or worse, completely unravels its own logic.
Wow.
And when that happens, or when a random GPU out of the thousands simply burns out and fails, the whole system crashes.
So to prevent starting completely from scratch, the engineers had to constantly checkpoint the training.
They had to capture and save the exact state of all 175 billion parameters at regular intervals.
You were talking about halting a supercomputer to write petabytes of data to a hard drive just so a random power fluctuation doesn't wipe out weeks of progress.
Exactly.
Which brings the financial reality into sharp focus. The article estimates a single training run for GPT-3 costs between $4 and $12 million in pure compute time.
Every single time the gradients collapsed or a GPU caught fire, they were bleeding cash.
And this is what I don't get. If you're an investor or even the lead engineer, how do you stomach that?
It's stressful.
I mean, you have thousands of machines constantly breaking down. You're burning millions of dollars a week. And at the end of the day, you're just running a giant, unpredictable science experiment. The stress must have been paralyzing.
It would have been paralyzing except for a monumental shift that happened behind the scenes.
Right.
They stopped treating it like an unpredictable experiment. They turned it into a math equation, thanks to the discovery of scaling laws.
Okay, the 2020 paper by Jared Kaplan. This is where the narrative shifts from alchemy into actual physics.
Yes. Kaplan and his research team at OpenAI analyzed the training runs and found definitive empirical proof that the performance of a neural network wasn't random.
It was predictable.
Very. It improved on a smooth, highly predictable curve based on 3 specific variables: the physical size of the model, the sheer volume of the dataset, and the total compute budget, basically how much processing power you throw at it.
Which is wild because prior to that paper, throwing $12 million at a bigger model was basically going to a casino and putting your entire company on black.
You just ran the machines and prayed the resulting AI was actually smarter.
Right. But Kaplan's math allowed them to forecast the future.
Yes. An engineer could plot a point on a graph and say, if we use exactly this many GPUs on this many tokens for this many days, the model will achieve exactly this level of accuracy.
They knew the outcome before they even turned the power on.
They did.
Which, I have to say, entirely vindicates Ilya Sutskever.
Oh, absolutely.
The chief scientist at OpenAI had this famous internal rallying cry of, just make it bigger.
Make it bigger.
Yeah. And from the outside, that sounds like pure Silicon Valley bravado.
Yeah.
But he wasn't guessing. The underlying mathematics of the scaling laws prove that if you simply feed the beast more compute and more data, it will inevitably become more capable.
The curves pointed up and to the right, to an almost eerie degree.
Sure.
But, and this is crucial, that predictably smooth curve on the graph masked something wild happening inside the neural network itself.
And here's where it gets really interesting. This is the anomaly that makes this whole deep dive fascinating to me.
Yeah.
The text points out that while the rate of the model's improvement was perfectly smooth and predictable, the nature of what the model could actually do was wildly unpredictable.
Yes.
The engineers started seeing spontaneous, emergent capabilities popping out of nowhere at certain scale thresholds.
Because, if we connect this to the bigger picture, the model was only ever programmed to predict the next token. That is its only underlying function.
Just guessing words.
Right. But as the network got massively larger, just getting better at guessing the next word forced the model to cross over into qualitatively different intellectual territory.
It had to get smarter to guess better.
Exactly. At a certain size, to accurately predict the next word in a bilingual text, the model suddenly taught itself how to translate French into English.
And at another threshold, to predict the next token on a programming forum, it taught itself how to write functional JavaScript.
Yep.
It figured out how to summarize dense legal contracts or perform logical reasoning entirely by accident. Nobody wrote a summarize function or a translation module.
No, the capabilities emerged solely as a byproduct of trying to minimize the error rate of predicting language at a planetary scale.
That is mind-blowing.
It is. But crossing those intellectual thresholds introduced a terrifying new problem.
Because raw capability is not the same thing as a useful product.
Not at all.
If you build an incredibly powerful engine, but you don't install a steering wheel or brakes, you haven't built a car. You've built an unguided missile.
And by late 2020, GPT-3 was profoundly capable, but fundamentally unsafe for public release.
Right.
It was a raw completion engine with no moral compass, no concept of helpfulness, and absolutely no preference for truth over plausibility.
It was the ultimate confidently wrong conversationalist.
Confidently wrong, exactly.
If you asked raw GPT-3 to explain a historical event that never happened, it wouldn't tell you the event was fake. It would use its massive mathematical power to generate a brilliant, highly detailed, perfectly fluent hallucination describing the fake event.
Because it didn't know you wanted facts. It only knew how to seamlessly continue the pattern of words you started.
So bridging the gap between that raw hallucinating engine and a cooperative tool required two distinct stages of behavioral alignment.
Right.
The first stage was instruction tuning. Instead of just feeding the model raw websites, the engineers started feeding it explicitly formatted commands.
Like a prompt.
Yeah, prompts like, translate this paragraph into Spanish, followed by the correct answer. This began steering the model away from aimless text generation and toward the concept of fulfilling a user's intent.
But instruction tuning wasn't enough to make it truly safe. They needed a second stage.
And the author rates this next engineering challenge as a 9 out of 10 in difficulty, placing it right alongside the terror of linking thousands of GPUs together.
Oh yeah. It's an acronym that became the holy grail of AI alignment. RLHF, or Reinforcement Learning from Human Feedback.
RLHF. Okay, how did that work?
Well, the underlying premise of RLHF is straightforward, but the logistical execution is a nightmare. Step 1 requires a massive army of human annotators.
Like real people sitting at desks.
Real people. The AI generates several different responses to a single prompt, and a human being sits at a computer, reads the outputs, and manually ranks them.
Ranking them how?
Like, option A is more helpful than option B, but option C contains toxic language, so it ranks last.
Okay, wait. If you've ever listened to a deep dive on automation, the irony here should be deafening.
Oh, it's hilarious.
You have the most advanced, exponentially scaling automated supercomputer on the planet, and to make it actually work, you have to bottleneck the entire operation through thousands of exhausted human beings, clicking A is better than B on a screen all day.
It is intensely manual labor. But those humans aren't directly fixing the base model. They are doing all that clicking to train a second, completely separate AI, known as a reward model.
Think of it like building a digital middle manager.
That's a great way to put it.
The base AI is the worker generating the text. But instead of the human boss trying to grade every single piece of paper the worker produces, which is impossible at this scale, the boss trains a middle manager to understand their preferences.
Right. The reward model's only job is to learn how humans judge quality.
Okay.
And once that reward model accurately mimics human preferences, the engineers run the base model through a reinforcement learning gauntlet.
The gauntlet?
The base model generates a response, the reward model automatically grades it, and the base model adjusts its internal weights to maximize that digital score. You are mathematically forcing the alien intelligence of the transformer to contort itself into shapes that human beings find helpful, polite, and safe.
But the fragility of this process is terrifying.
Extremely fragile.
Because if your human annotators get sloppy, or if your grading guidelines have unconscious biases, that bad human data permanently infects the reward model.
Yep.
And the reward model then forces those biases into the base model, ruining millions of dollars of compute time. The process engineering required to keep that human feedback loop pure is just mind-boggling.
It really is. And the output of that grueling alignment process was InstructGPT, which debuted internally in early 2022.
Right.
It was technically a smaller model than the raw GPT-3 with fewer parameters, but human evaluators overwhelmingly preferred its outputs. It was vastly safer, significantly more cooperative, and far less likely to hallucinate wild falsehoods.
So RLHF was the magic ingredient. It took a terrifying parlor trick and turned it into an enterprise-grade tool.
Exactly.
Which finally brings us to the very last piece of the puzzle. OpenAI had conquered an 8 out of 10 data pipeline, survived a 9 out of 10 infrastructure meltdown, and pioneered a 9 out of 10 behavioral alignment process. Now, they had to figure out how to put it in the hands of the public.
And here we arrive at the supreme irony of the entire 5-year saga. The only part of this Leviathan that the general public ever actually touches, the chat interface, is rated by the author as a 2 out of 10 in engineering difficulty.
At 2 out of 10.
2 out of 10.
From an engineering perspective, building the website was an afterthought. It's essentially a basic text box, a script to stream the text back word by word so it looks like it's typing, and a hidden background prompt that quietly tells the model, "You are a helpful assistant in a conversational chat format."
The technical effort to build the website was trivial. But the psychological impact of that interface was profound because it functioned as the ultimate abstraction layer.
It eliminated all the friction.
All of it.
Before that chat box launched on November 30th, 2022, engaging with a large language model required technical literacy. You had to navigate complex developer environments, generate API keys, and understand the arcane dark art of prompt engineering just to coax a good answer out of the machine.
Exactly. And the chat interface hid all of that behind a simple, familiar messaging screen. If you know how to text your friends, you suddenly knew how to command a supercomputer. And this raises an important question about how society judges the complexity of technology. We tend to judge it purely by how difficult it is to use.
Right.
Because ChatGPT was effortless to use, the world assumed it was effortless to build.
And that assumption fueled the explosion. It hit 1 million users in just 5 days.
Which is unprecedented.
Which, hilariously, instantly broke the system all over again. The engineering crisis shifted overnight, from the nightmare of training a model to the nightmare of serving it reliably to millions of concurrent users without the servers melting into slag.
Yeah, serving inference at that scale became an entirely new frontier of distributed computing, basically kicking off a whole new era of hardware optimization.
So what does this all mean? Looking back at everything we've unpacked from Aaron Rose's essay, the ultimate analogy he leaves us with ties this whole journey together perfectly.
It really does.
He argues that the original 2017 Transformer architecture was just a recipe. But ChatGPT is a 3-star Michelin restaurant that had to build its own private farms, establish its own global supply chains, and construct its own dedicated nuclear power grid just to keep the lights on in the kitchen.
Yeah.
Writing the recipe was a brilliant moment of inspiration. But surviving the 5 years of building and running the restaurant was an industrial miracle.
It entirely rewrites the narrative of the lone genius coding in a basement. The math provided the coordinates, but an army of exhausted, disciplined engineers had to physically pave the road day after day, crash after crash, to get us there.
If you're listening to this on your commute or at your desk, think about that the next time you type a casual question into that simple little text box. The machinery churning beneath that blinking cursor is unfathomably deep. But before we sign off, there is a lingering thought at the very end of this essay, a tease for part 3 that completely shifted my perspective, and we want to leave you to ponder it. We just spent this entire deep dive establishing that all of this staggering billion-dollar infrastructure was built to do exactly one thing: scale up a simple next word prediction engine.
Right.
But as the scaling laws proved, pushing that simple engine to massive scale spontaneously unlocked emergent intelligence that nobody explicitly programmed.
Which leaves us staring at a deeply unsettling question about the future.
Yeah.
If sheer scale is the singular force creating these unexpected leaps in cognitive capability, what happens over the next few years as we approach the physical limits of our global power grids and silicon manufacturing?
The hard limits.
Exactly. Are we meticulously mathematically engineering our way toward artificial general intelligence? Or have we simply constructed a machine that is about to cross a threshold where it begins teaching itself in ways we can no longer measure, predict, or safely control?
That is a wild, slightly terrifying place to drop the mic. Thank you for joining us on this deep dive. Keep questioning those simple interfaces because the systems hidden behind them are always deeper, messier, and far more complex than they appear. Catch you next time.